Okay, if you have a polynomial divided by a polynomial, so for example, take a look at this. You have a polynomial divided by a polynomial. No square roots. It is specifically a rational function. The first thing you want to do is check the degree of the numerator and the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, then it's time to turn to fraction decomposition. If it isn't, if the degree of the numerator is equal or greater in degree, like this one is, you're going to have to start with doing polynomial division, and then you might be turning to the integration technique of fraction decomposition. Now, the only fraction decomposition we've done so far is the non-repeating linear factors. When you have a repeating linear factor, so what this is showing is, for example, you have some linear factor to the third power times some other linear factor. The one that is to the third power, you need to have it to the first power, to the second power, and to the third power all together. But the thing is, if its base is a linear polynomial and you put in every power all the way up, you only need a constant above each one, and that's it. And let me actually just start with that one. And that's what example 4 is here to show us. But example 4 is starting with the problem of the numerator is not less degree than the denominator. So everybody, get out your pencils and pens. It's time to do some division. Woo! I'm not feeling the online excitement. I'm going to go ahead and do the box division. Whatever I'm dividing by, the x cubed minus x squared minus x plus 1. I'm going to put that over here to the side. The numerator polynomial needs to show up entirely in the interior of the boxes. And I'm starting with, in the upper left interior box, the leading term. From there, I'm trying to figure out what do I multiply x cubed by to get x to the fourth, and that would be x. Once I have that, I'm ready to multiply x times negative x squared, x times negative x, x times 1. Now, you might notice we don't have an x cubed term in here. That means that I need to be able to take this first pair of diagonals here. They need to add up to 0 x cubed. For that to happen, this is going to have to be a positive x cubed. Once that is determined, then I'm ready to figure out the next part of my quotient. What do I multiply x cubed by to get x cubed? And that would be 1. Then I'm going to go down the line and multiply all that by 1. When you are doing polynomial division, once your constant term shows up in the quotient, everything else that shows up inside the boxes to the right of that is all part of the remainder. So we need to now figure out what is going to make the remainder. This next group of diagonals needs to add up to make negative 2x squared. We already have that, so we don't have a remainder with our x squareds. We don't need any more. I'm just going to write that down. Then I'm going to look at my next degree down, and that is 4x. I need these three to add up to give me a positive 4x. Right now it's adding to make 0, so 4x is part of the remainder. All I have left is this 1, and what do you know? I don't need anything else. So my remainder, there isn't a whole lot to it, but that remainder causes this to be more complicated. So what do we get here? We get that this integral is the same thing as the entire polynomial of x plus 1 plus the remainder that we were not able to do division by that denominator. So just to take a step back, this is exactly the same thing as that. But what we have here is now something that is closer to being integrated. And that looks really sloppy. It's bugging me, so I need to try and make it look better. There we go, a little bit better. All right, we know how to integrate x plus 1. I'm going to come back to that. We need to figure out what to do about this. And so I'm going to grab that and move it aside. And that was x cubed. Okay. Now, we need to break this down. We can't just do a u substitution. If you notice you have a polynomial over a polynomial and u substitution isn't going to work, start looking at the denominator. Can you factor the denominator? I'm going to take the integral out of the way. When you're trying to factor a degree 3 polynomial, there are a couple of options in moving forward. You can try to find a number that you can plug in to make it equal to 0. I always try first a positive 1 and a negative 1. And also, I don't know if you're familiar with this particular factoring technique. It doesn't always work on third degree polynomials, but sometimes it does. If you group those first two and look at what factors out of it, and then look at the next group. Now with this group, it doesn't really have anything to factor out, but if you take a good look at this is x minus 1, and that's negative x plus 1. If I factor a negative 1 out of x plus 1, or negative x plus 1, I will get x minus 1. And what you have here is, over this subtraction, you have a common factor that can be pulled aside. And before this subtraction sign, I have an x squared left if I factor out an x minus 1. After my subtraction sign, I have just a 1 left over when I factor out the x minus 1. And this just happens to work really nicely. This trick doesn't always work. And sometimes you have to go to trying to find a number that you can plug into each of the x's to cause that to equal 0. And I'm going to move on from that and just keep going forward with this problem. So when I factor x squared minus 1, I see that I have 3 linear factors, but they are not distinct. In the past, if these were 3 distinct linear factors, then I would just do a over x minus 1 plus b over x plus 1 plus c over a different denominator. But when I have this, I can't just throw in x minus 1 a second time. If you look at that, it's like you might as well just combine those together because they're just one thing anyway, where a and c are representing constants. So what almost magically seems to work is if you make it so that you have the exponent squared on one of them. Now, what I want you to notice is if I take a look at these two together, just those two, if I was to go about a common denominator, I would need to multiply the top and bottom over here by x minus 1. And what I want you to see is that that causes this to be a quadratic. If a represents a constant and c represents a constant, then when I add these together, I am getting a degree 1 polynomial over a degree 2 polynomial. And so that allows me to use this technique to write this algebra in a different manner. As long as I began with a polynomial over a polynomial where the degree of the numerator was less than the degree of the denominator, then this will give me a new way to write that algebra. There are many ways to rewrite algebra. What fraction decomposition does is it gives us another way that it can be written, but it's not the only other way it could be written. It's just a way. And it's convenient for integration. So what you want to remember is, even if you have repeated linear factors, if the core of the linear factor, if the core of that denominator is a linear factor, you only need a constant above it. And I'm going to go back over to where I've shared this document. So this part A is looking at if each factor is distinct from the other, and they are all linear. As long as your numerator polynomial is less degree, this is a way to rewrite it. If you have any repeating linear factors, you want to write that core linear factor not just with the degree 1, but every degree up until you reach how many times it is repeated. In doing so, realize that that creates that you could bring all of these together. And in this specific situation, your denominator is going to be degree 3 when you do your common denominators. This has to be multiplied by ax plus b quantity squared to the top and the bottom. If I have a constant times a quadratic, that is going to create for me a quadratic numerator. And this one has to be multiplied by an ax plus b, making a linear numerator. So this isn't what you are doing, but I'm trying to explain why this is acceptable. It is acceptable to put just a constant above each of these linear core denominators. And it is sufficient to rewrite it, provided you began with a polynomial of less degree than the denominator. It creates a polynomial that is a minimum of 1 degree less than the denominator. Or I should say maximum. Yeah, maximum 1 degree less than the denominator. And that's what makes this an okay method. So, coming back to the problem at hand, it doesn't matter what order you write this trio in. And I want to emphasize that I've got the x minus 1 denominator. I have the x minus 1 quantity squared denominator. And then the other linear factor, x plus 1. Now here's what I'm going to do. This rational function must be equal to this for some trio of constants a, b, and c. And we're going to find that trio of constants a, b, and c. Here we go. I'm going to write this as an equation just like we did before. And you know what? I'm going to factor that denominator because I already know it's factored form. That must be equal to this expression. Now, if you remember when we're doing fraction decomposition, after we have come to determine how it's going to be rewritten with the unknown constants in the numerators, we multiply by the common denominator. And that common denominator is the x minus 1 quantity squared times x plus 1. These are going to cancel. And now we have 4x must be equal to, and then I'm distributing this over my addition. So as I'm distributing it, I get a times a cancellation and an extra x plus 1. Then I have plus b times a cancellation times an extra x minus 1 squared plus c times, this time the cancellation is with only one of the x minus 1s, so I still have another x minus 1, and I still have the x plus 1. Now, when we didn't have the situation of a repeated linear factor, we looked at the zeros of the original denominator, and we can still do that here. We're going to plug in the zeros of that original denominator. So that's going to be a positive 1 and a negative 1. That's going to allow us to find 2 of the 3 unknown constants. So let's do that. If I replace every x with 1, I'm going to get 4 times 1 equals a times 2 plus 0 plus 0. We know what a is. Then I'm going to plug in x equals negative 1. So over here I have 4 times negative 1 gives me negative 4 equals 0 plus b times negative 1 plus negative 1 gives me negative 2. Negative 2 quantity squared gives me 4 plus, and then I plug in negative 1 and I get 0. So with a little bit of arithmetic, I now know that b is negative 1. Now, here's what's different. I don't have a third 0. So here's what we get to do. We get to pick any number we want. We didn't have to use x equals 1 and negative 1. We could have used 3 x's that were not zeros of that original denominator. However, if we used 3 x's that were not zeros of the original denominator, we would end up with a system of 3 equations with 3 unknowns, and that is not pleasant. By using these known zeros of denominators, we're able to find 2 of our 3 unknown constants. And when I only have 1 unknown left, it's not that bad. We're going to pick any number we so desire that we haven't yet picked for x. So I want you to tell me, what x would you choose to plug in if 1 and negative 1 are already taken? And yes, this is your homework too. Zero is the perfect choice. When I plug in x equals 0, I'm getting 0 equals 1 times a plus 1 times b plus, and then I have negative 1 times positive 1, so I actually get minus c. I already know a and b, but I want to take a moment to show you, if you look at this equation with a, b, and c, if I had plugged in, let's say, 0 and then 2 and negative 2, I would have had 3 equations with a, b, and c, 3 equations that I would need to find the solution for, and that's not going to be fun, shall we say. But because I was able to find those other two, it's not too bad. So here we go. I'm going to plug in. We've got 2, -1, and that means my c is equal to a nice, pretty positive 1. Yay! Now, where are we at? We are just about ready to integrate now. I know my a, b, and my c. So that means that I have positive 2 over quantity x minus 1 squared plus b is -1, -1 over x plus 1, and then c -1 over x minus 1. I'm going to lasso this, and I'm going to move it. Oh, no wonder. I zoomed way out. I'm going to bring this back over to here. The integral that I wanted to solve started with x plus 1, and then plus, and I just rewrote what is circled there in green. This is now what I need to integrate. This is what I'm capable of integrating. Yes. Let me check. Did I mess that up? Oh, yes. Thank you. Yeah, I wasn't paying attention. Thank you, guys. Yes. Okay, I'm going to move this over just a little bit. Okay, this is what we are integrating. And now, this is the easier part. The fraction decomposition is a lot of algebra footwork, but once you get to the point of integration, if you had a linear core, the integration is pretty straightforward. But if you don't have a linear core, the integration could be more difficult. So you really want to get a linear core if you can. And by linear core, I mean when you factor it, when you have that multiplicity of a 0, or basically that exponent on a linear factor, that's a linear core, as far as what I mean by linear core. Those are going to come out really nicely. Use substitution is going to take it easy. So here we go. The integral of x is x squared over 2, plus the integral of 1 is x. Now, with this next one, I have the constant 2, and then I'm looking at a u substitution where my u is equal to x minus 1. When I put that in, I'm going to wind up getting 1 over u squared. That means u to the -2, so I have to use the power rule, and that gives me u to the -1 divided by -1. So ultimately I'm getting minus 1 over u, which was x minus 1. This next one is also a u substitution. For this one, the u is x plus 1. At that point, I am integrating 1 over u, and the integral is the natural log of the absolute value of u. And then u substitution of x minus 1, and we end up getting the natural log of absolute x minus 1. Yes.
I'm pretty sure that when you have the plus 2, shouldn't that be in the numerator of the fraction of x minus 1?
Thank you. I forgot it. Oh, I see what I did. I put the 2 down, and then I should have put times negative 1 over x minus 1. Thank you. And that gives us an answer. It doesn't look fantastic, but it's an answer. I'm going to pretty it up a little bit. I can actually bring these two together if I want. If I have a positive logarithm and a negative logarithm adding together, the positive logarithm creates the numerator, the negative logarithm creates the denominator using my log rules. Okay. Ah! How was that? Oh, okay. Anyway, your reaction. Fraction decomposition isn't too bad, but as far as taking up an entire page, I don't know if you want to hear this, but I'll say it anyway. These are not the ones who take up an entire page. These are the simpler ones. However, when you do integration in future in Calculus 3, it's unlikely that you're going to do the worst of the worst in integration. If that's a consolation. But as far as the integration that's typically done in a second semester calculus class, these are actually not too bad. However, this is the first time you're seeing it. And you're tired. And you've been online for a year and a half, almost. Okay. Now, the next type of example. Yes. Oh, thank you. Why is that the polynomial factors? Okay. Let me go back to the problem. Don't do that. So this denominator factors into x minus 1 times x squared minus 1. And there is a way to deal with this in this format, but the integration is always more complicated with a quadratic denominator. And with quadratic denominator, let me explain this. If I have to integrate 1 over x plus 5 quantity cubed, I can just do a quick u substitution of x plus 5, and suddenly it's something I can integrate. And the same goes with if that was x plus 5 squared. I could just do a quick u substitution, and I'm ready to go. But if my denominator is a quadratic, let's see, let me go with something that I know. If it's a quadratic that I am unable to factor, that actually doesn't have any real solutions to it, how do I integrate that? There are ways to go about integrating that, but none of them are as easy as doing a quick u substitution. If I am able to factor something down to a core of linear factors and not be stuck with a quadratic factor that is not a quadratic, there's a difference between integrating a linear to a power versus a quadratic that is not able to factor. And the point of the fraction decomposition that we're doing here is we're trying to create something that is easier or easiest to integrate, shall we say, or in a form that is nice to integrate or capable of integrating. Now, this does factor to x minus 1 times x squared minus 1. But I can factor that x squared minus 1 further. And anytime you can factor further when you're trying to manage integrating a rational function, you want to. And so with that, I brought these two together, and that gave us an x minus 1 squared and an x plus 1. And that is far easier to manage in an integration situation than this would have been as a denominator. Did that answer your question?
Yeah, I think when we did the fraction decomposition, the denominators, I think we accidentally squared x minus 1.
I'm trying to figure out where you're at.
Up there with a over x minus 1 squared.
Yeah. Uh-huh.
So I was wondering, because this is like a fourth degree polynomial, and the denominator was a third degree.
Oh. I think I know what you're referring to. Our numerator was a fourth degree polynomial in the beginning. So what we had to do was first do the polynomial division, which I erased part of it, but the polynomial division brought us to, what was it?
I understand that, but with the a plus b plus c part where we decompose the third degree polynomial.
Right.
So if you look at the denominators for those three, because it's like x minus 1 squared plus x plus 1. Wouldn't the denominator for all those three be a fourth degree polynomial, not a third degree polynomial?
Because of the repeating, This x minus 1 is already accounted for. So if I look at this, if I was doing a get the common denominator, this would need to multiply by x minus 1. This would need to multiply by x minus 1 squared. And this would need to multiply by x plus 1. And then I've got, oh, I'm missing one. This needs to multiply by also an x plus 1. So that's giving me a degree 3 denominator because of the fact that x minus 1 is here to the degree 1 and here it's to the degree 2.
Okay.
Does that make sense?
Kind of.
Okay.
After class.
Yeah. In fact, let me make sure everyone's clear on that. I'm going to go back to the beginning and let's make sure we understood what just happened there before moving on to another type. I'm just going to how about we restart the problem and look at it again? Does that sound like a good idea? Just try and get all this out of the way. All right. Okay. The first thing that we had to do was divide these two polynomials. And actually, since I did it the one way, let me do it the long division way this time. So x to the 4th minus 2x squared plus, I need to do division, but I'm just breaking this down. So then I need to multiply by x so that x cubed times x gives me the x to the 4th. But I have to distribute the x through all the terms. So that gives me minus x cubed minus x squared and plus x. And I'm subtracting that. So then x to the 4th minus x to the 4th, negative 2x squared plus, oh wait, that gives me x cubed does not add with the 2x squared. Then the negative 2x squared adds with the positive x squared, giving me a negative x squared. And then the positive 4x and the negative x and the positive 1. Then I'm looking at what can I multiply x cubed by to give me x cubed. And then I'm going to take that 1 and distribute it. But I'm subtracting. And I'm going to add the opposites. So then adding together, these two add up to make 0, these add up to make 4x, and then these add up to make 0. So when I do the division, I'm rewriting this integral as an entire polynomial of x plus 1 plus, and then I still have that denominator. But now I only need to put the remainder of 4x above it. So my 4th degree polynomial over a degree 3 polynomial. When I went through the division process, I had to get a remainder that was less than degree 3. It could have been degree 2, but it wasn't. It ended up being just degree 1, and that's just what it turned into. But this x plus 1 is the full quotient without the remainder part of doing that division. Then I'm able to integrate this function, and integrating that gives me x squared over 2 plus x. But then I still need to integrate this. And so we took something that was a degree 4 polynomial over a degree 3 polynomial, and after division, we got this, which we could take care of. But now what I'm working with is a degree 1 polynomial over a degree 3 polynomial. And so that's my new focus, is trying to rewrite my degree 1 over my degree 3. So at this point, this isn't in a form where I can nicely see how it's going to integrate. And I'm able to factor that denominator into an x minus 1 quantity squared times x plus 1. And I need to rewrite that polynomial, or I'm sorry, I need to rewrite that rational function into a format that I'm going to have an easier time integrating. So what I've got is, this is the integrand that I'm now trying to work with. And what you want to realize about fraction decomposition is, first of all, there are many ways that this can be rewritten. Fraction decomposition presents a way that it could be rewritten. It's not the only way it could end up being rewritten, but it's a way. And as long as this numerator is less degree than this denominator, I can do the fraction decomposition on that. And what I want to notice is I have this repeated factor. And with that repeated factor, that creates a possibility of a denominator of an x minus 1 quantity squared. I could have also had a denominator of an x minus 1 and a denominator of an x plus 1. So if I were to look at the idea of adding these three rational expressions together, these are my only possible denominators that I could have had, where this is the denominator that I get when I add them together. This pair right here, if I have only a constant above each one, when I look at this pair, and I just ordered A, B, and C differently than I did before. But what I want you to be able to see is, with this format, when I go through the process of common denominator, which is not what I'm doing, I'm just pointing out why this is acceptable. If I needed to make that common denominator, then when I multiply by this x minus 1, this is quadratic now. And so if I were to add these two together, I would have I said quadratic. This is a degree 1 polynomial plus a constant over a degree 2 common denominator. So as long as this allows me to create a 1 degree less numerator than the denominator, it is an acceptable form of how it could have been written. Now, everybody, wake up, pay attention, wake up, pay attention. Is everybody with me? So, for some of you, you want to understand why it's working. I want to take a moment to put in the bottom line of, if you don't tremendously care why it's working, what do you need to do? Make sure you understand that if you have a linear function to a power, you are able to break it down as that linear function to whatever power you have, another denominator of that linear function to the power of 1 less, until you reach that exponent 1, like we did here. This is an acceptable way of rewriting the original rational function. Then from here, yeah?
Miss Parker, can I have a question?
Yes.
Why can't we just do like, I don't know, like why can't we just do x minus 1 in one of the denominators and
Mhm.
x minus 1 in another?
Okay.
X minus 1 squared.
Okay, let's take a look at that. If this is what I have, these two can be combined to give me a plus b over x minus 1. A plus b, if a and b are both linear, or I'm saying two, if a and b are both constants, then this is itself just a constant, and let's call it d. And now all I have is just those two, and it's not enough to create this. Yeah. Okay. So, yeah, we're out of time.
Real quick.
Yeah.
I see why that one works, but you can't have just an x minus like all three of them.
Mm-hmm.
Why couldn't you have one with x minus 1 squared in the denominator and one with the x plus 1 in the denominator? Like, don't have
That is a very good question. If I have an x minus 1 squared denominator and an x plus 1 denominator, for a degree 2 in a denominator, a lesser degree would have to be a full linear. This right here is a viable way to go about it. It's not going to create, it's not going to necessarily create an integral that's easier to work with. Actually, it will create an integral that's easier than previously to work with, but not as easy as the one we created. Because if we end up using this format, we're going to have to then split the numerator and create two of these in order to get through the integration. So what you want to realize with fraction decomposition is there are different ways to rewrite these. We're looking for the way that is going to achieve the easiest integral. And that's kind of the bottom line. So we're going to need to talk about this more on Monday, obviously. And how about I just give you I'm debating what to do with homework because I want to quiz you guys, but you may want to do some review before the quiz. So I'll give you a few problems to do for homework over the weekend just to prep you for that quiz and make sure that you know what you need to know with what we've been doing. Alrighty? Okay. Head to homeroom.